We will solve this problem. A smooth pipe, 30 cm in diameter and 90 meters long, has a flush entrance and submerged discharge. The velocity is 3 meters per second. If the fluid is water at 15 degrees Celsius, what is the total loss of head? So this is the illustration of the problem. The pipe is a smooth pipe. Then let's have this as our reservoir A, and this will be our reservoir B. Then we are going to find the total head loss or total head loss as stated in the problem. Since the entrance is flush, so let's have this as flush entrance, and the discharge is also submerged. So the coefficient loss at the entrance is equal to 0.5, and the coefficient loss at the discharge is equal to 1.0. Then again, we will find the total head loss of the pipe. So for our total head loss, it is equal to the friction loss plus the summation of minor losses. So we will consider the minor losses, where minor losses is equal to, or the summation of minor losses is equal to the head loss at the entrance plus the head loss at the discharge. So your total head loss is equal to the friction loss plus the head loss at the entrance plus head loss at the discharge. For the pipe friction, we will use, based on the given data, or for the pipe friction loss, HF, we will use the formula of Darcy-Weisbach equation, which is equal to F times L times V squared over the 2G. Then, first we will determine the Reynolds number, or the NR. The formula based of our given. So the water is at 15 degrees Celsius. So for water at 15 degrees Celsius, the kinematic viscosity is equal to 1.139 times 10 to negative 6 meters squared per second. So our formula is equal to dV over the kinematic viscosity. So this is 0.3. For the diameter, you have 30 cm. So in meters, that is 0.3. Then the velocity is also 3 meters divided by 1.139 times 10 to negative 6. So 0.3 times 3 divided by 1.139 to the exponent of negative 6. So the Reynolds number is equal to 790,166.813. So this is greater than 2,000. So the flow here is turbulent. Okay. Our pipe here is a smooth pipe where your E over D is equal to 0. So, the relative roughness of our pipe, okay, since the pipe is smooth, so the relative roughness is approximately equal to, okay, equal to 0. For the friction factor, we will use Colebrook-White equation or the chart, which is the Modi diagram. Okay, for Colebrook-White equation, we have 1 over square root of F is equal to negative 2 log times E over D divided by 3.7 plus 2.251 divided by NR square root of F. Since the relative roughness for smooth pipe is approximately equal to 0, so you have 1 over square root of F time equal to negative 2 log 2.51 over NR square root of F. We will substitute the value of the Reynolds number to the equation. So, we have 2 over 51 times 790, 166.813 square root of F. We will use our calculator to solve this problem. So, 1 square root of F is equal to negative 2 log times 2.51 divided by 790, 166.813, then square root of F. So, by shift solve, using your calculator, your F is equal to 0.00121. We will use 3 significant numbers in getting the friction factor F. Since we already have our friction factor F, we can substitute this value to our friction loss formula. So, your friction loss is equal to 0.0121 times the length of the pipe is equal to 90 meters. So, you have 90 meters. Then, the velocity is 3 meters. Then, the diameter is 0.3 meters times 2G. So, 0.0121 times 90 times 9 divided by 0.3 divided by 2 divided by 9.81. So, the answer is 1.665. 1.665 meters. Okay. For the entrance loss, this is your HE. This is equal to the coefficient loss at the entrance times the velocity head. So, our entrance is flush. So, it is equal to 0.5 times the velocity. It is 3 squared divided by 2G. So, your head loss at the entrance, okay, you have 0.5 times 3 squared divided by 2 divided by G. So, you have 0.229 meters. For the discharge, okay, for the discharge loss, so let's have this as our HD. So, KD is equal to 1. So, that is 1 times velocity head. So, your velocity is 3 squared divided by 2G. So, your HD is equal to 0.4459 meters. So, you will substitute all of these head losses to this equation for our total head loss. So, we can say HL is equal to, friction loss is equal to 1.665. Then the entrance loss is 0.229. Then the loss at the discharge is 0.459. So therefore, head loss is equal to, so 1.665 plus 0.229 plus 0.459. So this is equal to 2.353 meters. So this is our answer. Okay? So the total head loss in this problem is equal to 2.353 meters. I hope you understand, and thank you for watching this video. Thank you.